In this segment, we'll take a look at the TCP and UDP protocols for a few minutes. Drag over the objectives of, again, Network Fundamentals Objective 1.2, compare and contrast TCP and UDP protocols. So let's get going with that so we can take a look here at them. TCP is known as a reliable protocol, reliable because we've talked about acknowledgments. It has sequence numbers, acknowledgments, and retransmissions for data that doesn't get there. It puts the byte stream into segments, the transport segments, and the application does not chop the stream into packets. The packets are going to happen at the network layer. Flow control. Different devices are going to operate at different rates. An older machine, older computer is not going to be able to accept data at the same rate as a brand new server that's operating at peak efficiency that we just put in, and versus our our laptop that we've had for 15 years. It's not going to be able to accept that data. So that's what we're going to do, is to create a sliding window. And for the sliding window, I got a little demo here. A sliding window is going to go down the line, and we're going to start out here with a window size of 4. The devices will negotiate a window size, and obviously the bigger the window size, the more data you can get. We'll start out with a 0% loss. Speed 5 is just how fast this thing's gonna go here. We can start this and we send our data A, B, C, D. It moves on down. This is where we acknowledge, and then we acknowledge D, and it moved on down the line. Keeps going down, and if we have no loss, it's pretty straightforward that we go from point A to point B, but you can see the window moving down with the data. Let's go in here and let's bring this thing up to, let's make a 30% loss. We're going to start A, B, C, D, E. We're okay. Well, we go back down. Okay, and we got F, and it's acknowledging D. It says, okay, send E and on down. So now we keep moving down the line, but we're still waiting. We're acknowledging F, so it's saying send G again, and here we go. So now we got G, and we should be able to, and now we acknowledge J, and the window moves on down the line. So kind of a little demo of how the sliding window works for the data and the data acknowledgement that we go through. If we bring our Wireshark back over here, bring it back up, let me drag it in here, and I got DNS. Let's go back to, let's look at TCP in this thing as we were before. Here we got some acknowledgments. 443. The 56778 to 443 tells me we got an HTTPS connection. We said that we can look at this thing. We can follow the TCP stream here. Doesn't make a whole lot of sense when we look at it, because HTTPS tells, or 443 tells us HTTPS, it's going to be secure. It looks like we got an Android down here, but the data obviously encrypted. Doesn't make a whole lot of sense when we go through here. Let's go down here and see if we can find TCP that is, let's go up and see if we can find a TCP that's not 443. Let's see if we can find an 80. May not be able to. Here is a client hello, a server hello, and there was certificate exchange when we go through here. But all of these are encrypted, but we can put the byte stream together in this particular piece of software. When we look in the TCP, actually we look at the whole thing. We have a frame, bytes on the wire, 528 bytes, 66 bytes captured for a total of 528 bytes on interface 0, which is Ethernet 0 in this particular system that we're going in. Ethernet 2 cell, the source is Dell 1C:9BE4. This is the MAC address, the hardware address. And when we do this, the del here is the equivalent of the first half of this, and then the 1C:9BE4 is going to be the serial number. Each manufacturer is issued organizational unit identifiers, OUIs, so that they use this prefix on all of their devices. Belkin down here, same thing. The first half is going to be a Belkin. And then we have the destination and the source. Let me turn the pen off and keep looking at this packet. The destination here, address, globally unique address, factory default, individual address, unicast, different switches that are available in here. And then we have the type. We talked about that. The type here, IPv4. When we're talking about the LLC, the logical link control. The internet protocol in here, the differentiated services, if we had one, this is going to be when we do a class of service, when we control who gets how much bandwidth, for instance. The flags here, we talk about fragmentation. We can do reserve, don't fragment, or more fragments. That's all that we can have in this thing. And this one is marked, it's got a 1, it's marked to don't fragment. If we had more fragments, it would tell us what the offset is. We're in the packet that thing fit into. Time to live 168. The protocol, next layer up, transport layer, TCP 6, TCP protocol, and protocol number 6. So when we close that one and get to the TCP portion, the source port, my ephemeral port from my machine, and kind of the way that just me, and that I have dumb ways to think about things, but when we think about this, it's kind of like making a phone call, and the whole thing's like making a phone call with the send, the SYNAC, hello, this is, and then we have the conversation. But the source port is, and the destination port, like phone numbers. If you're going to call a specific individual or location, you have to go to dial that phone number. You can call from any phone. So the source port from our machine can be any port. The destination port has to be the one that represents that service that we do. And then we have the sequence number here and the acknowledgement number 0. We haven't done anything yet. Flags that are built into this thing, the send set. This is the send. There was no data in a send packet, obviously. It's called the phantom byte. That's why it increments by 1 in the send and the SYNAC and all that stuff. Window size, 65,535. How big are we going to make the window, the sliding window, so that we can send the data as we go down it? Options, maximum segment size, no operation, different parts, different elements of the TCP protocol that we can see in Wireshark. And if you want, I would recommend that you go ahead and download Wireshark. It's free. Install it on your computer and watch a little traffic on your own network, just to kind of get an idea of what's going on these things. So we looked at a byte stream and segments. We can put it back together. Flow control, the sliding window we looked at, a little demo, and the fact that we had a window size in the packet that we used with Wireshark. Multiplexing port numbers, we can have multiple port numbers running at the same time on these things. And then the connection oriented, TCP was connection oriented to send, the SYNAC, and the ACK, the three-way handshake, allowed it to be connection oriented and reliable. Reliability because we send the acknowledgments to acknowledge receipt of the data. TCP is a full duplex protocol. Full duplex, we can transmit and receive at the same time. So things that we've already talked about and we looked at here: the transport, the send, the SYNAC, and the ACK, the three-way handshake, and then the acknowledgement of the data. And the transport layer, It's where this thing runs a layer from data from the upper layers, breaks it into smaller units, the segments, the transport segments, which we talked about in the OSI model module, passes to the lower layers and ensures that all segments arrive correctly at the receiving end by numbering them. If they arrive out of order, it can put them back into proper order. And we can also ensure that everything that we send actually gets there. Sequence number to each segment, we looked at that in Wireshark. Relatively large number is not the 0, 1, 2, 3, 4 like you see in the little example illustration on the left there. Much larger numbers that we use with that. Responsible for error correction and sending acknowledgments at the network level. So we're going to acknowledge receipt of the data and ask for resends if there's a problem with it. All of these things are going to have a CRC of some sort of cyclical redundancy check that's going to test to check to see if there has been a damaged packet as it goes from one point to the other. The TCP header, the header information, each of the layers of the OSI model adds its own header to it. So what we wind up with is a whole lot of overhead trying to get a little bit of data to a specific location accurately and in a timely manner. But in this thing, we have the source port and the destination port. Source port, ephemeral port, random port, temporary port, lots of different terms you'll hear. A destination port is going to represent a service that runs at the application layer, a web server, HTTP, an email server, POP3, or a mail or a SMTP, simple mail transfer protocol, SMTP, different services, FTP, that could be running there. We have the sequence number that we talked about. The acknowledgement number is the prior sequence, the one that we had with the amount of data sent. So the acknowledgement number is based on the amount of data that we have, and then we looked at some of the switches that were there, the control flags that are available. Maybe we really didn't look at the control flags. Let's see. Yeah, here we go. When we have those reserved and it's not set, NOTS is a number used once. Congestion window reduced, echo, urgent, acknowledgement, push, reset, and the reset's kind of like a hang up. Send, and that's what this one is a send, and then a fin is a finish. So we have the send to start the connection and the fin and the FINAC in order to complete the connection, to tear down the connection in an orderly manner. Window size, we talked about a checksum is used to ensure that this information hasn't been modified en route. Checksum, cyclical redundancy check, different things. The algorithm runs or uses the information that's within the header and creates a digit, a checksum, 2 byte, a digit, a 2-byte number, and then the same process gets run at the destination, and the two are compared to see that nothing happened. An urgent pointer here, 2 bytes. An urgent pointer says typically we're going to wait until a buffer gets full before the data gets sent. The window size that we talked about, fill up that whole thing. What the urgent pointer says is don't wait, go ahead and send the data. If you were streaming, I don't know, maybe stock prices or something like that, you would use an urgent pointer in order to not do that. UDP, connectionless, sometimes called an unreliable protocol. There are no acknowledgments. It is a much smaller packet. We'll look at the header here in just a second. Usually used for streaming, because if you're streaming something, let me bring this up while I do this, and let's see if we can find a UDP package here. UDP is a DNS, but Internet Protocol, UDP, we just have a source and a destination port. And DNS is domain. This is a lookup for a record to try to find the IP address. Queries at googlenews.google.com, and then we're going to get an IP address for that. We'll talk about DNS in more detail later on, and we also have flags that we set on it. Different flags than we had in TCP, and this tells me that the request is in this other packet. So we could go back to 27, the one right before it. This is where the request would occur in this. But this is a much simpler header. Ethernet, we have all that. Internet, UDP. Instead of all of the source port, we have source and destination, but the sends and the ACKs and the are not in it. We only have source destination port. Much simpler header that goes in it, and this is the header itself. We have a port, source port, destination port, UDP length, and then a checksum, and then the data is going to be connected to it. So UDP, user datagram protocol, connectionless, sometimes called unreliable. TCP, connection oriented. Reliability, because we do acknowledgments of the data. This is a table that compares the two, TCP versus UDP. General description: UDP, high speed, low functionality. TCP, full featured protocol. Reliability is its hallmark. Connection setup: UDP connectionless, TCP connection oriented with a three-way handshake. Interface of the application: message based. UDP has discrete packages, and UDP is stream based. Sends the data without regard to structure. The structure is a responsibility on down the line. Reliability and acknowledgement: UDP is a best effort delivery, whereas TCP is acknowledged. Retransmissions: UDP is not done. In TCP, the missing is resent. Data flow management: there is none in UDP. Sliding window in TCP. Overhead in TCP, or excuse me, UDP is very low. It's low in TCP, but higher than is in UDP. Transmission speed very high in UDP, and then high for TCP, but lower than the UDP protocol. Data quantity suitability: small to moderate, and then small to very large for TCP. The reliability for the UDP protocols typically is going to rest with the application itself. It's not like that it just, okay, too bad, so sad if it doesn't get there. The application, TFTP server is an example. If you're downloading configuration files or the operating system files from a Cisco switch or a router, if the download doesn't happen, then the TFTP server software will have the error messages. No resend. You've got to look at it and then redo it yourself. But the application can help you out there. Some common ports that I just threw in here, and if you can get these obviously on the internet. Some of the ones that would be handy to know: TCP 2021, FTP, the service is FTP, Secure Shell, Telnet, SMTP. These are a whole bunch of good ones. TFTP. To know, and to know whether they are which transport protocol, TCP or UDP. So kind of a common ports. If you want to look at the RFC, they're over here. And then represent application layer services, where we have port 20 and 21 represent TCP that's running, or TCP, FTP that's running at the application layer. TCP is going to be the transport protocol that goes with FTP. And if we go down here to 69, TFTP, UDP, it's the kind of the poor man's version of FTP. Is a simplified version of FTP, not nearly as robust as the TCP protocol. So with that, what we've looked at is TCP. We looked at the header. It's a more complex header. We have the send and the acknowledgments, and we have reliability, and reliability based on the synchronization. Connection oriented with the three-way handshake. UDP was connectionless, had a much smaller header, and we didn't have any reliability with it. I didn't really want to do that. So with that, that takes care of the TCP and UDP. The next topic, and that's what I was opening this for, the next topic is infrastructure components, and we'll see you there in the next segment when we talk a little bit about some hardware. A couple pieces, actually 3 pieces of hardware. Actually, we'll do more.